What if the secret to building the sustainable homes of the future was hiding in plain sight? What if it was in the wood we usually just throw away? Today, we're going to dig into how this overlooked timber could totally revolutionize the way we build.
It sounds a little wild, doesn't it? The idea of taking wood that's been labeled as too weak or too full of knots and using it to build the very walls that keep us safe. But believe it or not, that is exactly the radical idea that some brilliant engineers are looking into right now.
So, why is this so important? Why even bother with this bad wood? Well, it all comes down to a huge problem that the construction world is facing. Let's call it the timber squeeze.
Okay, so here's the deal. On one hand, our demand for timber is just skyrocketing, right? We want to build more houses, and we're trying to use sustainable, low-carbon materials to do it, which is great. But, and this is a big but, on the other hand, the supply of that really good, strong, high-quality wood is actually shrinking. Things like fast-growing plantations and the devastating effects of bushfires are taking a toll. We've got a serious mismatch on our hands.
And here is the absolute core of that supply problem. To keep up with demand, pine plantations are growing trees incredibly fast. And when you do that, a typical log that's, say, 30 years old can be made up of more than 70% juvenile wood. And that's the weaker, less dense wood from the tree's younger years.
So that brings us to the star of our show today, low-grade wood. But it is so important that we understand what this term actually means, because it's not quite as simple as just being young wood.
See, low grade is basically a performance rating. Think of it like a report card. A piece of timber gets this label if it just doesn't meet certain targets for stiffness and strength. And the reason for that could be anything. Too many knots, a weird grain direction, or even some flaws that show up when the wood is dried out.
So, let's just make sure we're crystal clear on this. All that juvenile wood we talked about is weaker, for sure. But low grade is the official stamp a piece of timber gets if it fails the strength test. A log with a lot of juvenile wood is much more likely to be graded as low quality, yeah, but even mature wood can get that label if it has enough other flaws.
Okay, so this is the crucial point. What do we do with this massive, underused resource? We can't just keep tossing it aside. Instead, engineers are coming up with some truly clever strategies to basically upcycle this weak wood into high-performance building materials. It's awesome.
And the solutions, they generally fall into three main buckets. You can reinforce the wood, basically by adding stronger materials to it. You can laminate it, which is where you combine several weak boards into one super strong beam. Or you can use a bunch of smaller pieces to create these large, really robust panels.
Let me show you a fantastic example called the lamb stud. The process is so simple, but it's incredibly effective. You take 5 low-grade boards, you glue them together into a solid block, and then you just slice that block up into brand new studs. The end result is a product that can meet or even beat the design values for a standard piece of timber, all because the flaws and weaknesses get spread out and averaged away.
Reinforcement is another really powerful strategy. I mean, check this out. By bonding just a thin plate of a strong, lightweight material, think of something like fiberglass, onto a low-grade beam, you can jack up its stiffness by up to 55%. That is a huge improvement.
And for a solution that is just brilliantly simple, you've got nail laminated timber, or NLT. Forget all the expensive glues and fancy presses, you just nail layers of boards together. It's a cheap, fast, and really effective way to turn a pile of low-value boards into strong, large panels you can use for floors and walls.
All right, so these engineering tricks sound pretty clever on paper, but do they actually hold up in the real world? That, my friends, is the ultimate test. This is the big one, isn't it? If we actually replace standard structural wood with this out-of-grade timber in a typical house frame, is it going to be strong enough? Can it handle everything from the weight of the roof to the crazy force of a powerful windstorm? To find out, researchers did just that, but virtually. They created these super detailed 3D models of 2 very common house designs. Then they swapped out the standard pine for timber with the measured properties of this out-of-grade wood. And then they threw everything at it. Gravity, the weight of people walking around, realistic wind loads, all simulated in some seriously powerful engineering software. And the results were fascinating. For most of the house frame, the little pieces between studs, the plates at the top and bottom of the walls, the low-grade timber held up perfectly fine. No problem at all. Even the main wall studs were totally safe when it came to pulling and bending forces. The only area that raised a little bit of a red flag was compression. That's the force that tries to crush the studs from top to bottom. And you gotta see this. For most parts of the house, the low-grade timber wasn't just strong enough, it was way, way stronger than it needed to be. I mean, look at the wall plates. The actual stress they were under was just a tiny fraction of their real strength. This proves that in a lot of cases, we're using premium, high-grade wood where we absolutely don't need to be. And that's a huge waste of a valuable resource.
So, the science checks out, the computer models look really promising, but there's still a pretty big gap between a successful simulation and getting this stuff onto a real construction site. We have to talk about the final hurdles. Yeah, because when you talk to builders and engineers, the people on the ground, you start to hear the same concerns over and over. They worry about the wood twisting and warping, which is a massive headache on a job site. There's just not enough hard data or official certifications yet. And honestly, there's just a natural resistance to moving away from the materials that they already know and trust.
But here's the good news. A path forward actually exists. It's what's called a performance-based approach. It starts with really tough testing of the material to prove exactly what it can do. Then, a qualified engineer has to sign off on the design. And the final, golden step is getting a Codemark certification, which is basically an official stamp of approval saying this product meets the national building codes.
And this, right here, is the key takeaway from all the research. The study concludes that there is a clear regulatory pathway. It is not a dead end. Through the right testing and the right engineering oversight, this overlooked material can be proven to be safe and effective enough to be used in our homes.
So, when you really think about it, this isn't just about wood anymore. It's about a whole new way of thinking. It's about seeing the hidden potential in the things we already have and then finding smarter, more intelligent ways to use them. So the real question isn't, can we do it? The real question is, are we ready to build it?